Okay, in lecture 21, we're going to talk about a confluence of a few different topics that we've already started to discuss. In particular, we're going to talk about phase transformations, interfaces, and conservation. Okay, so to do this, let's consider two systems that we've already studied to some extent. So let's think about two different phase transitions. So in particular, let's think about the Ising system, so a magnetic phase transition, versus the regular solution. Okay, so we're going to think about these two. Now, of course, what's happening in these two systems is quite different, right? In the Ising system, you have magnetic order, and so we're thinking about the spins associated with different atomic positions and the way that these can align or anti-align at different points in the system. And so flipping one spin from being pointed in one direction to pointed in another direction isn't necessarily related to what's happening to the spins next to it. So the Ising system would be an example of a non-conserved order parameter. And what we mean by that is that you can flip a spin, you can change the number of spins, and that doesn't violate the rules of the system. You can change the number of upspins by flipping an upspin to a downspin or vice versa. It's not a problem. Whereas in the regular solution model, we have lattice positions that are occupied by different species, right? And so in order for a species to change, right, it has, at a particular site, it has to move into that site. That is, you can't just change the number of, let's say, A atoms at some particular site, so change a B atom to an A atom without bringing an A atom from somewhere else, right? Because the composition of the system is basically fixed, right? So here we have a conserved order parameter, right? And the composition, so the composition could change locally, but overall it has to be conserved, right? Okay, but in other ways, these systems are very similar, right? So they're similar in their underlying thermodynamics. And in particular, we'll just recall that if we look at the Ising system at zero applied field, so here let's draw some axes. So this is going to be as a function of m in the Ising system, or as a function of composition. Let's see, so this is m for the Ising system, or xb for the regular solution model, and we're going to plot either f. In the Ising model, we were looking at the free energy. In the regular solution model, we were looking at the Gibbs free energy. But if we look at the free energy, the appropriate free energy, as a function of the appropriate control parameter, for T greater than some critical temperature, and here we're going to assume that we have no external field in the Ising model, but at some high temperature, we have a monotonic free energy as a function of either m or composition with a single well-defined minimum, right? So in this case, where we have a single minimum, right? And then if we go below some critical temperature, so T less than Tc, and we plot the same free energy, right, as a function of m for the Ising model or xb for the regular solution model, then we get a change in the shape of the free energy where suddenly there are two minima, right? And so that's what typically accompanies phase separation, right, in these systems, right? So in the Ising model, this would cause you to have domains of plus and minus spin, right? So you'd get spontaneous magnetization. In the regular solution model, this would cause you to have compositions that were optimized, and so you'd get phase separation. So, although the interpretation is different, the free energies as a function of the order parameter, so m or xb, is similar. But we know that this leads to different things in the Ising model, since the order parameter is not conserved, m can change to become one of the minimized values. But in the regular solution, since the order parameter is conserved, right, it can't just move to have a composition that's at the minimum. The system phase separates. And thus satisfies the constraint of a fixed overall composition. Okay. Right. So the difference would be if you, let's say, started with a composition in the middle, right? In either case, in the case of the Ising model, this would just simply change over time to become minimized, whereas like in the regular solution model, you would phase separate into two phases, right? Okay. So in that case, it would, some of the system would go this way and some of the system would go that way. Okay. So we want to talk a little bit about how the system moves from one phase to another. And so let's first think about the Ising model. So in the Ising case, right, we said the magnetization can shift continuously from m equals 0 to m not equals 0, right? So if we consider the case where we impose so we could start, let's say, at t less than t0, start at t less than tc, and consider when we don't have a minimized H field, and then we would have a free energy that would look like this, potentially, such that maybe we started at some m that was minimized before we imposed the H field. So let's say we were down here at this minimum, then we applied the external magnetic field, and now when we look at F as a function of m, we'd really rather be at this minimum, but to do that we have to move over this bump, right? So in order to minimize the free energy, we might need to first increase the overall free energy, right? So we would, in order to get from this, which is not the global minimum, to this, which is the global minimum, we'd first have to increase the free energy, right? And so this implies that there has to be some fluctuation where the free energy first goes up before it can go down. And so we want to look at the details of how this might happen in our system. How might you nucleate this second phase, create this second phase, even though small amounts of change in m lead you to actually increase the free energy.